All right, let's talk about one of the coolest, most dramatic things you're going to see in precalculus. We're talking about these invisible walls that functions get super, super close to, but can never, ever touch. We're talking about vertical asymptotes. And that quote, it just nails it. This isn't just some random line on a graph. It's a hard boundary, a place where the function just goes totally haywire, either rocketing up to positive infinity or just diving straight down to negative infinity. It defines the absolute limits of the graph. So, what are these things really? How do we even find them? And, what do they actually tell us about the shape of a graph? Well, that's exactly what we're going to break down today. Okay, so here's the official scoop. But honestly, I love the idea of a force field. Imagine this invisible line at some x value, we'll just call it c. As your graph gets closer and closer to that line, bam, the y values just go nuts. They either shoot straight up forever or plummet straight down. So you might think finding these invisible walls is going to be complicated, right? But it's not. It's actually a super simple two-step recipe. Seriously, it works every single time. Okay, now listen up because this is so important. Step one is where almost everyone messes up. You have to simplify the function first. I'm talking factor everything and cancel out anything that's the same on the top and bottom. Why? Because those things that cancel out, they're holes in the graph. Totally different from asymptotes. Then once you've done that, step two is a piece of cake. You just take whatever's left on the bottom, set it to 0, and solve. Boom. Those are your vertical asymptotes. All right, let's see this in action. First up, a pretty straightforward example. We've got f of x equals x plus 1 all over x times the quantity x minus 4. Okay, step 1, simplify. Can we? Let's see. Step 1, simplify. Can we? Let's see. Nope. Nothing cancels out here. So we get to jump straight to step 2. We take that denominator, x times x minus 4, and set it equal to 0. And what does that give us? Well, either x equals 0 or x equals 4. And there you have it. Just like that, we found our two invisible walls, the vertical lines at x equals 0 and x equals 4. Okay, that was a good warm-up. Now let's look at one that's a little trickier, where the asymptotes are kind of hiding from us. We've got this function, g of x equals 10 over 2x squared plus 6x. Now, this is exactly why step 1 is so important. You can't just set that whole bottom part to 0. You gotta factor it first. So what can we pull out of 2x squared plus 6x? Well, a 2x, right? That leaves us with 2x times the quantity x plus 3. Now we can set each of those factors to 0. 2x equals 0 gives us x equals 0, and x plus 3 equals 0 gives us x equals negative 3. See? By factoring, we revealed those hidden asymptotes. Okay, so we're getting good at finding the lines, but that's really only half the story, isn't it? The next question is, what does the graph actually do when it gets near one of these walls? Does it shoot up like a volcano, or does it plunge down like a bottomless pit? Believe it or not, the answer is hidden in plain sight. It's all about the exponent on the factor in the denominator. We call that the multiplicity, and it's like a secret code that tells you everything about the graph's behavior. It's simple, really. If the exponent is an odd number, like 1, the two sides of the graph go in opposite directions. But if the exponent is an even number, like 2, both sides go in the same direction. It's that easy. Okay, let's put this new rule to the test. Check out this function. H of x is 1 over x minus 3 squared. So what's going to happen around its asymptote? Well, first things first, let's find the asymptote. We set x minus 3 equal to 0, which gives us x equals 3. Easy enough. Now, what about that exponent? It's a 2, and 2 is an even number. So ding, 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 that's our clue. It means both sides of the graph have to go in the same direction. And think about it. Anything squared is always positive, right? So the denominator, x minus 3 squared, is always going to be a positive number. That means y is always approaching positive infinity on both sides of that line. It's like a chimney shooting straight up. All right, let's switch gears for a second, because I want to talk about the common traps people fall into. Seriously, if you can just avoid these two mistakes, you've basically won half the battle. Okay, mistake number 1, confusing holes and asymptotes. We've talked about this, but it's so important, I'm going to say it again. If a factor cancels out, it's a hole, a single missing point. A factor that stays on the bottom, that's your asymptote, a whole line. Got it? Cool. Now the second big mistake, this one's all about how you write down your answer. This is so simple, but it costs people points all the time. Look at this. You can't just say the asymptote is 5. What is 5? It's just a number. An asymptote is a line, a vertical line. And how do we write the equation of a vertical line? We write x equals 5. You have to write the full equation. That's the correct way to do it. So I know what you might be thinking. This is cool, but it's just, math for a test. But what if I told you that these invisible walls, these vertical asymptotes, actually show up in one of the most mind-blowing, most extreme places in the entire universe? No, I'm serious. In physics, when you look at the equations that describe the insane gravitational force near a black hole, you find a vertical asymptote. And this isn't just a line on a page. This mathematical boundary has a real name. It's the event horizon. It's the point of no return. As something gets closer and closer to this asymptote, the equations show that time itself stretches towards infinity. So to us, watching from far away, it would look like time for that object just stops, literally stops. How wild is that? This abstract idea from your pre-cal class is actually describing a fundamental law of the entire cosmos. It just makes you wonder, right? If something as cosmic as a black hole is defined by a vertical asymptote, what else out there is? What other things in the real world, in economics or biology or engineering, might be secretly governed by these same mathematical force fields, these points where things just explode to infinity?